everyone, my name is Xing. I'm a high schooler currently in my 11th year, so 11th grader high schooler from La Jolla in the United States. And today my project is going to be called an Immersion Campus Simulation Protection and Safety Improvement System using Artificial Intelligence and Machine Learning, revolutionizing school emergency preparedness with virtual reality. So first of all, I would like to thank everyone for letting me present here. I know I'm just a high schooler, so it's a little something new for me, but that's okay. So starting with the presentation for today, this is going to be my research project. So I would like to start with a brief introduction. So in today's world, crisis scenarios such as fires or active shooter incidents have become a critical concern, impacting people in schools, workplaces, and public spaces. Responding effectively to such threats can be challenging, especially in high-stress environments where quick decision-making is required. The project addresses the need for a virtual training platform to help users learn and practice survival skills in these hazardous situations. The goal is to build a realistic, immersive scenarios that simulate crisis environments and help individuals build situational awareness and decision-making skills under pressure. So first, let's look at some numbers from the United States. So fire-related incidents and active shooter events have left lasting impact on communities globally. According to the National Fire Protection Organization in America, there have been approximately 353,100 residential fires each year in the United States alone, resulting in nearly 2,620 deaths and 11,030 injuries. So as you can see, I don't know if you guys have been keeping up with the news. For example, in Los Angeles, in America recently, there has been a massive fire that has completely burned out basically half of Los Angeles. And these are the really big wildfires that start unexpectedly and people need to learn how to evacuate from them. Next up, we have another problem that is very prominent in America specifically, and these are rising cases of active shooter incidents. So similarly, active shooter incidents have risen alarmingly, with the FBI reporting 50 incidents in 2022, a 97% increase from a decade prior. These incidents underscore the need for individuals to be better prepared and to react effectively and quickly. So as you can see, my game basically takes a lot of these current huge basically problems in the US, and we're going to solve that basically, or at least help the situation. So the importance of training tools like this go beyond individual preparedness, as they empower communities to respond more cohesively during crisis, potentially saving lives. And while simulations alone cannot prevent such incidents, they can help users gain confidence and situational awareness needed to navigate these threats. And by offering an engaging interactive experience, this project aims to equip individuals with essential survival skills that may be life-saving in real-world situations. So for example, a couple of these issues with the drills that we have in the US, for example, we do things such as fire drills, in which at a random point in the day, at a random point in the year, we are going to hear the fire alarm go off in our school. And what ends up happening is that students have to evacuate from the field. Now, this is our current solution to fire drills, but how can we improve this? First of all, let's start by stating the problems with fire drills. Fire drills give off many really negative side effects, such as increased anxiety and stress. For example, fire drills just start randomly, and there are these huge blaring alarms that just sound in the middle of class. And especially if students have things such as past trauma, this can increase the amount of anxiety and stress in this situation. And this is something we do not want, because not only is it a negative impact on a student's mental health, it can also greatly impact their experience of school and have them basically have this kind of anxiety throughout the day. Next up, we have desensitization. So this is becoming an increasing problem, especially in the US. Since schools do fire drills pretty much 2 to 3 times a year in America, what ends up happening is that every single time there's a fire drill and the fire alarm goes off, students immediately assume that it is not a real emergency. For example, even if our school has an undeclared fire drill, when students are walking out, they're going to be saying things like, oh, well, the popcorn just burned, it's fine, or oh, something just caught on fire in the chemistry lab. They don't really think it's an actual fire, and they're not really attentive, and they don't really care that much because they're simply just too desensitized to it. They don't think it's an actual fire, and that's why drills are becoming a problem. Because now that if there's an actual emergency, students are just going to be like, oh, it's just another drill, and they're not going to take it seriously. Next up, another problem is disruption to learning. So this occurs especially when in the middle of class, a fire alarm goes off. Usually teachers have to plan around this, but especially if teachers aren't aware that a fire drill is going to happen, they might have important pieces of curriculum, say before a test, that they have to go over. And they just simply might not get to that because there is a fire drill. And especially with fire drills, people filing out of classrooms, getting to the fields, and eventually coming back, you basically have 30 minutes of basically wasted time that could have been dedicated to learning. Next, we also have lack of realism. During an actual fire emergency, people are going to panic. People are not going to remain calm, and that's a problem with fire drills. Because of my earlier point of desensitization, due to the fact that fire drills are way too common, what ends up happening is that people don't think it's the real deal, and they just assume it's a drill. And so they're just going to calmly and slowly walk in a single file line to the field. If there's a fire in the building, this is not going to happen. Say there's a fire right outside the door. You're not going to stand in a single file line and just walk at the door. You're going to run out screaming. And all this chaos that ensues is just simply something that drills do not cover. Next, we also have to be inclusive of special needs students. Things such as fire drills do not include this. For example, a special needs student who needs a wheelchair, for example, might use the elevator during a drill because it's simply too inconvenient to bring them down the stairs. However, during a real emergency, this will not be the case because those elevators might not be working, and that is a huge problem. So in this case of fire drills, we do not include special needs students, and we actually need to do that because that also improves the chance of getting all the students out safely. Next, fire drills also create a false sense of security. This also goes back to my desensitization point because since due to the fact that we have these drills so often, we often always assume it's a drill and we feel safe, we feel secure that we know what's going to happen. We know how to act during drill and we think that because we do well during drills. However, like I said, when there's an actual fire, you're not going to stand out and be organized. You're going to run out screaming and there's going to be so much chaos that's going on. And as a result, we currently have this false sense of security and we cannot keep having that because it will only impact us negatively in the future. And finally, we have unintended behavioral issues. Students who, for example, have past trauma, especially with drills such as active shooter, not just fire drills, but active shooter drills, students who might have to deal with past trauma with gun violence, for example, might have like more more exaggerated reactions when it comes to these drills because it will stimulate their past trauma and as a result will be detrimental to basically their own sense of thought and will not keep them thinking straight for the rest of the day or maybe even the rest of the week. We have to keep the not just the ability to save people's lives, but during these drills we also have to keep the students' mental state in mind, and that is extremely important when you have a drill. So how will we fix this? Not exactly fix, but how will we make the system better? So my current project, Immersion Campus Safety Simulation, Protection and Safety Improvement System, basically builds a realistic immersive scenario and simulates life-threatening incidents such as a fire outbreak or an active shooter. Currently, my game currently includes a fire outbreak, an active shooter, an earthquake, a flood, etc. We're also planning to add more emergencies in the future. So we have these kinds of emergencies, and basically this is going to be a virtual reality game. And this offers an engaging interactive experience because it helps individuals build real-time decision-making skills under pressure. And this not only equips individuals with essential survival skills, but it also saves lives. So first, judges, let me introduce my project a little bit to you. So my project essentially is a virtual reality game. So it's a game that when you have your virtual reality headset on, you can end up doing things such as trying to escape. So every single time you enter a certain emergency, for example, a fire emergency, you're going to get into your virtual reality goggles and go into the environment, and a fire is going to start either in the room that you are in or in a space around you. And when you're in the area with the fire, your job is to escape the building and run to the field. Now, we simulate this through multiple ways. For example, we have NPCs in my game currently. We have NPCs to simulate the amount of people in a classroom. So it's not just you alone evacuating. You have to evacuate with a group of people that are very chaotic. So we have NPCs to simulate that. In addition, this virtual reality game also offers a very engaging and interactive experience because you can actually see the flames. You can see the fire spreading. And that's what's important. When you have something such as a drill, there's no fire, there's no panic, and as a result, it's just not effective. When you have a virtual reality game, this is not only an engaging interactive experience, you can also help them build more real-time decision-making skills. Now, during an actual emergencies, there are all sorts of anomalies that could happen, and teachers simply might think they're too prepared for that, but in reality, they're not. And when there's an actual fire coming at you in virtual reality, this can help them basically stimulate what to do in a scenario. For example, if an NPC falls down, a teacher has to go help them up. And so how are you going to do that without blocking the hallway? These are the kinds of real-time skills that you have to learn in the case of an emergency, because these skills can save lives. In addition, we equip these individuals with the essential survival skills. For example, how to effectively escape the building, or in the case if the field is on fire, where do you go? Not the field, obviously. So as a result, from my virtual reality game and through these characteristics, I can fully basically improve the environment of drills. So next up, let's talk about what I used to build this virtual reality game. So as I mentioned earlier, it's a virtual reality game which requires a headset and two controllers in your hands. And I use Unity, the Unity engine to basically code this, and I use C# for my computer language. So I use C# and Unity, and for the graphics, basically, I downloaded some 3D prefabs from the Unity asset store, and I used that. In addition, I want to talk about one more component of my game, which is artificial intelligence. Now, judges, you might be wondering, why does this project name start with the words machine learning and artificial intelligence? Well, let me explain that to you. So, for example, NPCs. NPCs are all powered by AI, and that's extremely important. But the most important NPC in my game is probably in the active shooter emergency scenario. Because during the active shooter emergency scenario, you have to have an active shooter to basically simulate the current environment. And so as a result, the active shooter is a very specially programmed AI that can basically chase down the user, and also when the user is hiding, not notice the user. So I'll mention more about my code later, but this is going to be my AI component in this game. Not just the NPCs in the other scenes, but actually the active shooter itself. And this not only creates a more realistic environment, it also makes sure that this game is basically one player, which is more convenient for the user. So first of all, let's talk about a couple of challenges I had in my project process. So as a quick overview, my challenges that I had were problems with the code for fire spreading and implementing functional doors and maintaining performance. So let's start off with talking about fire spreading. So one significant challenge with my script called fire propagation is ensuring that the fire spreads realistically without overwhelming the game's performance. The system must identify and ignite flammable objects near the player without causing excessive lag. Unity's physics.overlap sphere could be used to detect nearby objects, but frequent checks across large areas could slow down the program. To solve this, a coroutine might help engage and manage checks over time instead of all at once, and this maintains both accuracy and performance. Additionally, implementing an ignited tag on flammable objects could reduce redundant checks, ensuring that the fire only spreads to objects that haven't been already ignited. So that's my first problem with the fire spreading is the lag due to Unity's code with the physics.overlap sphere. My second problem was implementing functional doors. Since functional doors are challenging because when it comes to integrating door frames and handles, specifically realistically within a virtual reality environment, this can be extremely challenging. For example, having the door hinge, so the door turns around the door hinge, or using a door handle. So when you pull the handle with your controller, the door swings open on its hinge. This part was extremely hard to code because not only do you have to define the door hinge, you also have to make sure the door handle links well and works properly. So imported doors from, for example, the Unity asset store often have problematic hinges or blocked player movement, and these hinges simply are too problematic to be used, and this creates difficulties in passing from one room to another. So one solution could be to design a door with a hinge mechanism that adjusts the transformation properties rather than physically rotating, and this allows for smooth access without disrupting the player's flow. In addition, we can add colliders around the doorframe to ensure that the walls properly block movement when needed, and while experimenting with a first-person controller instead of a virtual reality could offer an alternative if a virtual reality specific door remains inconsistent. So that's my problem with implementing functional doors in my solution. So next we have maintaining performance. So maintaining performance across multiple scenes, especially when navigating fire-prone areas, is essential to prevent redundant scenes from impacting optimization. In other words, reducing scene switches by maintaining a consistent XR rig could be an efficient solution so that player data and settings remain constant across scenes. An effective approach could be using it could involve using a button-based navigation system from the main menu to direct players to specific scenes based on their choices. And by reusing the XR rig, it's possible to streamline the experience without reinitializing assets each time, and this optimizes the performance without compromising immersion. So these are the three challenges I encountered during my process of making this game. So next, I'm going to talk a little bit about structure. So the structure, as shown by the flowchart up here, is from start screen to scenario selection to scenario execution. So let's start with the structure. So the structure of this virtual reality crisis training program is designed to immerse users in a realistic crisis scenario, combining three main components: scenario selection, scenario execution, and outcome evaluation. The program begins on a start screen where users are introduced to available training scenarios, and upon navigating to the scenario selection screen, users can choose between crisis scenarios, such as fire evacuation or active shooter survival, and this is tailored to develop specific response skills. And once a scenario is selected, the program moves to a scenario execution. In the fire evacuation scenario, the user's entry into a room triggers fire propagation, and the user must navigate through obstacles to avoid burns. The active shooter scenario involves situational awareness and evasion techniques, while with the user finding and utilizing hiding spots to remain undetected. And both scenarios feature dynamic elements controlled by Unity's physics and coroutine systems, making them effective and useful, basically. And in terms of the environment is responsive and immersive. And prefabs with colliders are used to establish interactive objects, and distance check algorithms allow the fire and shooter to respond to users' action in real time. Finally, the outcome evaluation displays user performance statistics, such as the number of burns or successful evasions. Users can choose to return to the main menu or replay the scenario, offering opportunities to improve their response skills. Created in Unity, this program utilizes physics-based mechanisms, coroutines, and prefab interactions to ensure a seamless, performance-optimized experience. The structure flow from scenarios to outcome evaluation supports effective training and skill reinforcement. So let's go on to the scenario execution. So the scenario execution component immerses users in real-time crisis training where they interact with dynamic environments. Implemented with Unity's physics and coroutine systems, this component uses distance checks and prefabs with colliders to simulate fire propagation and active shooter evasion. Coroutine-based timers control interactions, enhancing responsiveness and realism. So let's jump into my code. So one program that I had in my fire scene is called fire propagation. So in my fire propagation script, you can see it to the right. It's coded in C#, and it has a couple parts. So for the first part, it's called IEnumerator, which is my coroutine. So this function basically allows you to create a timer that's based on another game's action. And in this situation, a coroutine is spreading fire based on where the player lands. So for example, if the player lands in room A, let's say, that means the fire is going to start in room A. If the player lands in room B, then the fire is going to start in room B. And the moment the player lands in the room, a timer is going to start on the top left corner of your virtual reality screen. And all you have to do is evacuate the building within that time. As you evacuate, however, the fire is going to continue spreading, which brings me to my next part called physics.overlap sphere. This is a built-in function in Unity, and basically this is a physics thing that comes in the Unity library. It's a physics basically application, and everything that is a prefab has a collider attached to it. So everything that's a prefab in my game, for example, chairs, tables, the actual fire, a door, a window, the building, etc. These are all prefabs, and they all have colliders attached to them. This makes them tangible objects in the game. And since all these flammable objects have colliders on them, I also tag them with a specific tag called flammable. So when the fire starts in one room, for example, room A, when the fire starts in room A, any object, any prefab in there that has the tag called flammable, is going to be able to catch on fire. So for example, if the fire starts in the middle of the room and there's chairs on the edges, whichever chair is the closest and whichever chair is a certain distance away from the fire is going to spread to that chair because the chair is tagged as flammable. If, however, something like a water bucket is not tagged as flammable, the fire physically cannot be ignited on that water bucket. So it might be all around the bucket, but it will not be on the bucket because the bucket is not tagged as flammable. And so something else that the physics.overlap sphere function does is that it checks the distance between different colliders. So for example, if a chair and another chair, since they have their own box colliders, when these colliders are close enough, then the fire spreads from chair 1 to chair 2. However, if these chairs are far enough, then the fire will not spread to these chairs because they are too far for the fire to spread and the colliders are not close enough. And this is if the object has a flammable tag. So lastly, we have the flammable.isIgnited tab. So this is actually a boolean, and this boolean is called isIgnited because there is a setting for all the flammable objects. So if it's not ignited, that means it's false, and that means when we send the fire to flammable objects in a certain distance, it is turned on and set to true, and as a result, the fire starts burning on the objects. So next up, this is one of these scripts in my active shooter scene, and it's called player hiding. So player hiding is basically when the player is going to hide from the NPC active shooter. Now in the game, the player can hide in multiple spaces. They can hide in desks, they can hide under chairs, they can hide in locked rooms, etc. They have multiple options on where to hide. Now how the script for hiding works is through different parts. So for example, the for loops and iterates. So the for loops iterate through the hiding spots and the transform function function basically is a list of hiding spots. And there is a area where we set up the camera on here on line 50 of my code. And basically when we set up the camera, this is going to be important because when the player is hiding, the camera has to move down. So for example, if they're hiding, if they're regular, for example, if their camera is regularly 5 pixels above the ground, when you hide under a desk, it has to be shorter than that because you're hiding under a desk. So the camera becomes shorter, and also this also checks the distance between the main camera and the hiding spot. If the camera is very close to the hiding spot and you hit a certain key on your keyboard or hit a certain key on your controller, your camera will automatically go under the hiding spot and you will be able to hide. However, if your camera is too far, then you will not be able to hide. And something else that the camera does is it will check that the distance between the main camera and the active shooter is a certain amount of pixels away. If the active shooter is too close to the main camera, then the player basically has to go game over and they have to start over again. And another thing about this is the hiding spots. So if a hiding spot is basically available, then it is turned on in the variable called is hiding. This is also a Boolean, by the way. It'll be turned on, it'll be turned to true on is hiding. And if hiding is true, then basically the NPC, that is the shooter, will ignore the player and keep moving along his set path. As a result, you will have if you are hiding, then the NPC will not notice you. And if you leave the hiding spot, then the is hiding variable is going to be set to false, and the NPC shooter will now be able to recognize you. So moving on to my last piece of code is called count burns. This is still in my fire scene, the scene with the fire evacuation, and this basically is supposed to count the amount of times you've been burned. So for example, if the player camera hits any of the fire prefabs that are burning on the chairs, the floor, etc., then your burn count will go up. And once your burn count hits a certain level that you can set yourself, in my case, I set it to 5. Once you've been burned 5 times, it's game over. So what I use for this is a function called onTriggerEnter, and this is also a function that Unity provides for you. And this basically goes on the fire prefab. So anything that's a fire prefab has this function attached to it. And so this basically checks whether or not an object hits the player tag. And if it does, a sound effect plays and it subtracts the number of allowed burns by 1. So for example, if I'm allowed 5 burns and I touch a fire on accident, it's going to go down to 4. And once I hit 0, I'm going to go game over. And so in the scene data class, we have a value called burns, and that's just an integer. And so if it is a number of burns that you're allowed to have before you lose the game. And every time you hit the fire object, it subtracts by 1. And this also includes my too many burns function, which checks up if we use all our burns. And it checks if our scene data value for burns is 0. If too many burns checks that our scene data value is 0, then that means we have been burned too many times, and we have to initiate the lose screen, the game over screen, and it will reset our burns back to 5, and also restart the game. So these are my count burns functions. So next up, some of the experiments I conducted in my research. I'll be going over this by stating purpose, variables, experiment, and then data on my next slide. So for my experiment number 1, so my purpose of this first experiment is to assess the accuracy and efficiency of player responses, and basically focus on the effectiveness of movement controls. So, since this is a virtual reality game, I have a couple of options as to what to use for my device simulator. So the first thing is a device simulator, or if you might be familiar with the term XR rig, that is going to be my current VR thing. And also we have another option, which is an FPS controller, a first-person shooter controller. FPS controllers are also typically used in a lot of games that are already published today, popular games, and it is also a much smoother controller, but we wanted to test that in this experiment. So we wanted to ask, which one provides a more realistic and responsive experience, the device simulator or the FPS controller? So what are the variables we're going to be measuring in this experiment? We're going to be measuring the time to completion, the accuracy of response, and user perception of realism and control. So the experiment we're going to be conducting is that 10 randomly selected participants will be navigating 2 scenarios, both the active shooter scenario and the fire evacuation scenario, using both control methods. So each person is going to use both the device simulator and the FPS controller. And these results are going to determine whether adjustments are needed for the simulator or if the FPS controller should be recommended for optimal training effectiveness. So this is going to be our data table. So this is the data table of the data I collected. So on the left side, we have the total amount of participants. These are the amount of people that we have participated. They were all randomly selected. And you can see that they're all being using the every other. So half of them are using device and half of them are using FPS. And this has our data right here. So this is kind of summarizing the actual data. So I have a list of mean and median completion times. The mean was 25.4 seconds and the median was 24.5 seconds. Our lowest completion time was 17 seconds, very fast. And our highest completion time is 36 seconds. Our average success rate is 81.5% and our median success rate is 88.5%. Our average realism ratings are 4.1 out of 5 and our range for realism ratings range from 3 to 5 and out of 5. So 3 out of 5 to 5 out of 5. So our results, our conclusion basically from this first experiment is that the FPS controller had a notably lower completion time and the highest success rates compared to the device simulator, and the FPS controller provided better control. The wide variation in these completion times was also very surprising to us because we thought that the difference in controllers shouldn't be that much, and that since it's the same game, they should have the same completion times. However, there was a pretty big variation, as you can see from our lowest and highest completion times in the data above. This most likely suggests that the device limitations in the simulator slowed participants down. So that means the device simulator was a more slower object. The XR rig didn't work as well. And this most likely originated from the simulator's slower response. The XR rig does take up more space to run, and this also emphasizes the importance of control precision for effective crisis training. So next up, we have our second experiment. Experiment number 2. So same format. So our purpose for this experiment is to assess user satisfaction with control responsiveness, scenario realism, and immersion. So our variables to be measured are going to be on the next page, but it's pretty much the same thing as the last one. Time it took to complete, and then ratings, and also what the people thought about it. So for our experiment, we're going to have 10 randomly selected participants complete both the active shooter and fire evacuation scenarios using a device simulator and an FPS controller. And they're going to gather feedback scores on a scale of 1 to 10 after participants complete each crisis scenario. So this is our basically table of our data that we collected, and you can see that our 10 participants are listed on the left, and our ratings are listed on the top, and then the three right corners. So moving on to my experiment data. So our data in terms of mean, median, lowest, and highest out of our 3 variables, control precision, scenario realism, and overall experience, we have the following. So for our mean ratings, our control precision is 7.1. Our scenario realism was 7.8, and our overall experience was also 7.8. For median ratings, we have control precision at 7.5, scenario realism at 8, and overall experience also at 8. For lowest ratings, we have control precision at 5, scenario realism at 6, and overall experience also at 6. And for highest ratings, we have 9s all across the board for control, scenario, and overall. So what are our results in conclusion from this? So our conclusion is that the FPS controller consistently received higher ratings, especially for controlled precision. And this indicates that it provided users with a much more satisfactory and immersive experience. And the lower ratings for control precision show that there were limitations in accuracy. In other words, the device simulator and the XR rig had limitations in accuracy, whereas the FPS controller was a lot better in terms of user basically friendliness. And that's why we basically want to try to use the FPS controllers in this case. So lastly, we have our conclusion. So for our conclusion, basically, it's just stating that some of the limitations of my project included the device simulator limitations, user control variability, and potentially high VR setup costs. As a result, the device simulator sometimes hinders accurate movement, and this affects the immersion and realism in high-stress scenarios. These glitches also hinder user experience in general. Improving control responsiveness is also crucial because implementing compatibility with more advanced virtual reality controllers would enhance accuracy. Additionally, incorporating a more robust artificial intelligence system to dynamically adapt to user behaviors would enrich the realism, ensuring that scenarios adjust to user decisions, adding depth to crisis training. So another limitation is setup costs. Now, virtual reality headsets are very expensive and they're also very hard to run. So to address this, I want to explore more lightweight virtual reality software alternatives that could run on budget-friendly virtual reality headsets, so people don't have to spend like $400, $500 just to play this game. This also increases accessibility without sacrificing immersion. Finally, adding a post-scenario feedback where users receive personalized tips based on their choices. And this basically would allow further improvement in learning outcomes. And with more time, testing across diverse user groups and optimizing the interface could also ensure broader applicability and accessibility across different crisis scenarios. In conclusion, this virtual reality-based crisis training project demonstrates significant potential to enhance emergency preparedness by combining immersive realism with interactive scenarios and addressing device limitations and control responsiveness, along with implementing adaptable artificial intelligence and post-scenario feedback. This would greatly improve and make more effective my game, and basically this also makes crisis training more accessible, responsive, and impactful. Thank you very much. That was my presentation.